Ever wondered how AI models really figure out what comes next in a sentence? Most of us think of tokens as fixed building blocks, like letters or words, but what if the model could learn how to split text on its own? Today, we're diving into a groundbreaking approach called the autoregressive U-Net, or AU-Net, which flips the script on how language models process information. Let's start with the basics. Traditional models like GPT or BERT use something called tokenization to break down text. Think of it like slicing a loaf of bread. You decide ahead of time how big each slice is. Byte pair encoding, BPE, a popular method, splits text into tiny chunks, sometimes even individual letters, then builds a fixed vocabulary of these pieces. But here's the catch. Once that slicing is done, the model can't adapt. It's stuck with those same chunks, no matter how the text changes. A U-Net changes that. Instead of predefining how text is split, it learns during training. Imagine a model that starts by looking at raw bytes, the digital letters of text, then gradually groups them into words, pairs of words, even chunks of 4 words. This creates a multi-scale representation, like a zoom lens that switches between close-ups and wide shots. Early stages focus on tiny details, while deeper layers spot bigger patterns like themes or ideas. Here's where it gets cool. The architecture itself is inspired by medical imaging tools called U-Nets, which rebuild images by first compressing them, like a photo shrinking, and then expanding them back. A U-Net does something similar. It compresses text into coarser representations, then expands them, injecting high-level insights as it goes. Deeper stages don't just predict the next byte, they anticipate the next concept. But a U-Net isn't the only game in town. Researchers are also testing 2 game-changing techniques, sequence packing and FSDP. Think of sequence packing like packing a suitcase for a road trip. Instead of leaving empty spaces between your clothes, you stack them tightly to fit more. In AI terms, this means organizing data so the model can process more information without wasting computational power. Then there's FSDP, or fully sharded data parallel. It's like splitting a huge puzzle among a team of workers. Each computer handles a piece of the problem, then they all share the results. Together, these tricks let models learn from massive datasets without getting stuck in a slowdown. Now let's talk about the models themselves. They tested 4 approaches: O-Net, BPE, Transformer, and Mamba. The big reveal. How a model breaks down text, whether it sees whole words or tiny character bits, makes a huge difference in performance. Take the Qt benchmark, which measures how well models can manipulate text, like rewriting sentences or spotting errors. Here's the twist. Byte-level models, which process text at the character level, outperformed others in certain tasks. It's like comparing a chef who chops veggies versus one who works with whole ingredients. Sometimes the finer details matter most. But here's the real kicker. O-Net isn't just another model. It's built with a hierarchical structure, like a team of specialists. Its parameters, think of them as the Model-S brainpower, change across layers. For example, one layer might handle 512 units of data, then the next jumps to 2048, and so on. It's like a relay race, where each runner specializes in a different leg. This setup lets O-Net tackle complex tasks more efficiently, even when working with smaller batches of data. And let's not forget the math behind it all. The total flops column in the data. That's a measure of computational power, like how many calculations a model does. A 1B parameter transformer might need 6.6 E20 flops. That's 660 quintillion operations. But O-Net's smarter design lets it do more with less. By using longer sequences and smaller batches, it's like driving a fuel-efficient car instead of a gas guzzler. So what does this mean for the future? These techniques aren't just about speed, they're about efficiency and adaptability. By letting models learn their own tokenization and optimizing how they process data, we're paving the way for smarter, faster AI that can handle the complexity of real-world language. The next time you interact with an AI, remember, it's not just guessing the next word. It's building a multi-scale map of meaning, 1 byte at a time.